The problem here is how to let go of the control. The solution that I'm proposing is treating this network of sensors kind of like neurons in your brain. It's an activation of multiple neurons together that collectively answer if there is an event of interest happening. My name is Cenek. I'm an assistant professor of computer science at the University of Alaska Anchorage, and my formal training is in machine learning, artificial intelligence that was applied in the field of complex systems. I'm investigating engineering and basic science question of how to monitor reliable power or communication networks for environmental or human events. So the solution for the problem is to use very simple low power sensors. And sensors in this case are very simple computers that they can be augmented with additional detectors. The detector could be a microphone, it could be a motion sensor, it can be gyroscope, you name it. Two motivating examples of this technology being deployed. One would be ice breakup. So ice breakup monitoring and predicting is a very hard and open question. We can see when the ice broke off and is floating, but it's hard to actually predict that something is going to happen unless we are listening to the ice creaking, moving. The second deployment scenario for this technology would be to detecting an inclusion and intrusion across a perimeter. So the sensors can listen to sounds of somebody walking through the network and collectively validate if the activation of the noise is telltale of somebody walking across the perimeter. For this project, the very interesting part is not to design the detectors, but to design the architecture of the sensors and how they talk to each other to basically detect whether or not an event is happening from ambient noise. They're locally connected. So they only see their nearest neighbor. So that's the architectural solution that I'm proposing, is somehow collectively they have to decide that the signal they read from the environment converts into an event that is worth reporting. First of all, it's decentralized, it's asynchronous. All of these sensors are reading and talking without having a common drummer saying, now you send, now you read, now you send, now you read. The scenario would be to deploy the network from a snowmobile or flying a UAV over second-year ice and then dropping the sensors in preset intervals that will result in grid. And then they start listening. Listen to the creaks of the ice, listen to the motion of the ice, and then comparing the creaks against what they were trained to recognize as, oh, this creak is because the ice is breaking or because there is motion. As far as I know, what we proposed, designed, implemented, and tested is one-of-a-kind solution that truly lets go of the control, truly lets go of the common clock, truly lets go of centralized aggregator nodes. And it was very exciting to see that the signal would automatically reroute and the network would self-heal. So that was a beautiful part, because as a truly biologically inspired solution, we're using not just the constructs, but the network has the same property as a biological system. So if the devices temporarily cannot communicate or process information, the overall solution, the overall network will self-heal and still be able to process information, to communicate.